object-oriented databases deal with key-value databases. And so essentially you're saying, here is a key, here is a value. For example, I could say, I'm interested in a particular person, and I want to know what kind of shoe that person wears, for example. What's the color of the shoe, right? Usually ladies are very interested in this kind of detail, right? So what's the color of the shoe? Most of the time I don't even know if I'm wearing a shoe, but, oh, it's a nice shoe, by the way, right? So absolutely. So you have a little collection of data that you can get into. Given a particular object, I want some properties about it. And I want to drill down into those details. So that is basically a key value pairs you're interested. You say, given this key, give me this value, please. Give its value. Then you say, well, I need a little bit more, by the way. Then let's go a step further. We'll give you a document database. So what is a document database? Given a key, I'm not going to give you a value. Given a key, you can hold a document. Now, the word document is a bit confusing. What's a document? A document could be XML, a document. Could be a JSON document. Could be a comma-separated value document. Could be another form of document. Could be a blob, a big, large binary object, right? So you could really come up with any kind of data that you want to. It is a document you want to store. So for every key, you are interested not in storing one value. For every key, you want to store a document with it. And so that can be supported, but that is a subtype, but it falls in the same category of having a set of key value pairs. Or it could be a column family database. What does that mean? Given a key, you have a set of columns of data. And you're saying, wait a second, given a key, you have a column of data. Haven't we heard that one before? Called relational databases? Yeah, but it's different here, because in a relational database, every column, every row has to have the same number of columns, right? So imagine I create a table of a person. And in a table of a person, what am I storing? I have first name, last name, and I have an email address. This is good. Everybody should have a first name, last name, and email address. And now what happens in this case? If a person has a first name, last name, and email, everybody is listed. And let's say for a minute, we have this data, and we are storing these two fine people in the front row. And now I realize, he says, you know what, Venkat, I would rather you store my date of birth as well. He's a brave man, he wants me to keep his date of birth in it. So now I create another column. I change the schema, right? And I said, first name, last name, email, and date of birth. And now she says, you dare not. I'm not going to tell you my date of birth, right? And so what do I do now? Now I have to say, oh, what do I do? Maybe DB nullable, right? Where does DB nullable come from? It comes from hell, right? And we have to deal with it in the code. And it becomes messy. And now every row must have every column or a DB null. Well, what if we say, you know what? His row contains first name, last name, email, and date of birth. Her row doesn't. She's all in smiles like, thank you, Venkat, not for asking that, right? So her data contains first name, last name, email only, right? And maybe shoe color. That makes her really happy, right? And he says, shoe color, get out of here. I don't care about it, right? So now notice, we got two rows, but the columns are not the same at all. And that's what a column family database gives you, is that it is column like a database, relational databases, but every row can have different sets of columns. And that gives us the flexibility, and you're not really forcing every row to conform to a predefined structure. Every row can have a combination of things it wants to have. And you say, you know what, hey, I like music. Okay, fine. You can have a columns for music you like, but the other person may like sport, and they can have columns for sports they like. So then, of course, they often are clustered, but they're clustered based on aggregates. Remember, we started talking about how scalability becomes an issue. How do you deal with scalability in these databases? The way we deal with scalability is, we are going to have all these aggregate-oriented, but we're going to put these on 3 different nodes, by the way. Node 1, Node 2, and Node 3. Node 1 is going to contain everybody here whose data is here. We're going to keep it in Node 1. Node 2 is going to contain the data for everybody here. Node 3. All these 3 databases are key value databases. However, my application, when the request comes into the cluster, I would say, whose data am I interested in? Oh, I'm interested in, a person Joe's data, oh, go to node 1. I want Raj's data, go to node 2. So in other words, I will keep an entire data for one aggregate in one node and yet another aggregate possibly in another node. But all the aggregate data is going to be in one node. How do we achieve the scalability, by the way? By distributing this data across nodes, but only in aggregates. So everything related to Joe is on node 1, everything related to Susan is on node 1, but everything related to Raj is on node 2, and I can have these distributed across. But somehow, when the application gets the request, it can know which way to direct it, and now we can have scalability because there are multiple machines serving it. Making sense? So this gives us an ability for us to scale through fairly well as against a relational database would. Now in this case, it's easy to navigate and organize the data going back and forth, and it's very hard, of course, to perform ad hoc queries. Why? Because, go ahead please.
How about the payload?
We'll talk about that in a few minutes. Good question. We'll talk about that certainly. Good, very good point. So, but it's very difficult to perform ad hoc queries. Oh, yes please.
But we have partitioning also in relational database.
Yes, you can.
We said that theses are programming tasks, but when we have a column family of databases, so we are introducing some kind of an uncertainty, right?
Aha.
So we don't know, like from a data access perspective, we don't know how many columns my keys.
Right.
So
Good question. Very good question.
it's not easing my programming task.
No, actually it does, but you have to kind of ease yourselves first. What I mean by that is, you are absolutely correct. But when you're saying it, in your mind you're thinking about the code you're writing, which usually is C++, Java, C#. But imagine for a minute that you have flexibility to use languages which are more reflective. Even Java and C# use reflection. But language like Groovy and Ruby, you don't bind yourselves to known types already. You can kind of walk up to it and say, what do you have, by the way? Now all of a sudden, you have flexibility to code. So we need to change the way we think, right? In a rigid world, you are told everything, right? So I usually make a joke. If you're a C++ programmer, and you are C++ programmer for life, and you retire and open a restaurant, here's how your restaurant will be. The restaurant will be with an open door, and somebody comes in, you say hello. And they say, so what do you serve here? You say, what do you mean, what do we serve here? Why did you come here without knowing what we serve here? Because in C++ you should know everything, right? You don't ask questions at runtime, right? If you're a Java programmer and you open a restaurant, people come in and say, hello, yeah, how are you doing? Great. What do you serve here? Let me tell you my menus here, please. What would you like over here? Right? But you can only order from the menu. But if you're a Ruby programmer, Groovy programmer, that's the kind of restaurant I want to go to. Right? I go in and say, how are you doing? Great. Can I show you the menu? I say, no, actually, let me tell you what I would like. Can you make the food for me? Which happens to me all the time, because I go to places where there is nothing on the menu I can eat because I'm a vegetarian. And I have to order off the menu. I say, let's talk about what I would like, please, because I'm the one who's going to eat. And that's the kind of restaurant I want, right? So notice the flexibility you get out of this. So you're absolutely right from the angle from which you view, you're saying, look, from the language I code in, but that's not the language we want to code in all the time, right? And the minute you get more reflective, either in Java, or you use libraries to do it, or you shift over to other languages on the JVM, for example, then you get more benefits. Great observation, by the way. But that's kind of the important thing to keep in mind, that it gives you that flexibility. So, but it's hard to perform these ad hoc queries. You will have to visit each of the related nodes to perform such a query. What does that mean? If I say, I want to relate Joe's data with Raj's data and do some queries related to it, timeout. That's not possible so easily. It's not geared towards that. It's not going to give you that kind of capability. And by the way, it only provides ACID within an aggregate. So if I commit data for Raj's data, no problem, I can give you ACID. If I put some data into Joe's data, I can give you the ACID. But if I'm updating multiple data, I cannot guarantee ACID for this. That becomes a problem. In the case of aggregate ignorant database, it's a graph database. What does that mean? We're more interested in the relationship rather than the data. You focus on how these data are related to each other, who knows whom, what did they buy, what are they interested in. And it's very easy to add and remove relationships. and you can also query on these relationships. So you're more interested in who knows whom and what do they do rather than a property of one object. So you're not more interested in the data for somebody, but more on relationships, right? This person is related to that person in this, and who is the cousin of that person, and what did they buy, and then you want to do things. So when you go to Amazon, for example, the customers who bought this book also bought. Hey, that's pretty cool. Now you can go look at other books that you can buy, right? So you're more interested in the relationships in here more than the data itself. Now, the key-value databases, of course, are really dealing with data itself. I mentioned this earlier. And as a result, you're more oriented toward just focusing on giving this one data value in a key. It could also be a blob, but the most important thing here is you're not really performing many queries. Given a key, here's the data. Good luck, by the way, right? Hey, can I ask you? No, you cannot. Here's the data for the key. You're done. It's your problem now. The database doesn't run many queries. Doesn't mean there won't be a variation that does, but as a theme, given a key, they'll give you a value and say, I'm done, right? That's my job. So that's the focus of those. They don't go any further with this. And think about this as a bucket of data. That's what hash tables do, right? Hash tables store data in buckets using a hash code. So in the same way, given a key, you would bucket it across different implementations of the cluster. We haven't talked about the failover yet, but I'll come back to it. So what are some of the implementations of this? Berkeley DB, DynoDB, HamsterDB, Memcache, Project Voldemort. So there are quite a few interesting set of databases that do. What kind of data would fit into this, by the way? Session data in a web application, for example. Shopping cart, you could store into this. Think of a shopping cart. Why do you have to store a shopping cart in a relational database? There's no reason to. It is so transient in the sense that while they are shopping, right, it's persistent but only for a short amount of time. And it's not an enterprise data at this point, right? And user profiles and preferences, these things can be stored in this kind of database. So the first thing I want you to keep in mind is we're not telling you got to put everything here, right? People get paranoid and they say, oh my God, well, give me my relational database. No. You can still have your relational database. But you don't have to put everything in a relational database, something lightweight for these kinds of data, right? You don't have to use a relational database for these. Document databases can store documents like we talked about. It gives you the flexibility to access and query. You can even run a query on the values and do some, look for parts of the aggregate. You can say, look at this XML document and get me a child element from it. And of course, you have an ID and the document for you. Some databases in this area are CouchDB, Terrastore, MongoDB falls into this category, and a few others. What kind of data would you store in this? Logging information, for example, right? Blogs. Think about it for a minute. That makes a lot of sense, isn't it? Because what does a blog have? A blog has a title. A blog has a set of keywords. A blog has a content, some images. It has some links. And it's got comments, and comments to comments to comments. So this is all a hierarchical structure. Often we may store this in a JSON object or XML format, so it fits really well. And content management systems can fit into this as well. What about column family databases? Well, they of course store the columns, and we said that columns are not required to be consistent across rows. Columns can be grouped together as families. Simple columns are really columns which are simple in nature. Super columns, as they are called, are complex or aggregated columns. So this could be like an entire address field coming together, if you will. Writes can be logged and put into mem tables as well. So Cassandra, Hypertable, SimpleDB are examples of database that fall into this category. What would you use this for? This also fills the gap for things like logging, blogs and content management system. So you could either use the document database or this one, which again should make sense, right? Because you could still take a particular blog, and instead of storing it as a JSON object or XML document, you could store them as columns as well. Nothing stops you from doing it. A title column, a body column, a comment column, and then you can have comments to columns as ID references. You can store those, so columns can be used as well. And of course, you can have some queries on those as well. What about graph databases? Graph databases are more interested in relationships. So why don't we just look at an example of this? I'm just going to show you one example of a graph database. And let's say how this is going to look like. So here I'm going to use Neo4j, and let's just understand this particular example. By the way, first of all, I don't have any data with me right now, so notice there is nothing under my sleeves. All that I have in this directory is a Gradle file to compile and run this code, and I have a source directory where the source code is. That's all I have, nothing else, right? And of course the jar files. So what do I have here? I've defined a relationship type. A relationship type implements a relationship over here, relationship type, and I got two relationships. Programming in is learning, right? These are the two relationships I'm interested in. What am I programming in? What am I learning? So I have a create DB function that's going to create a new database, and I'm going to specify where to create the database in the DB path variable. I've created a database. I'm going to create a node. The node is going to take a property name, and it's going to take a value for the property, right? So this is basically the node values. So I create a set property on it and return a node for you. So what does a create data do? I'm going to create a bunch of data. I have created James, I've created Sarah, created Bill, using create nodes, and their property names are name, which is just a string, by the way, called name, and the names are these appropriate values. Then I have another three nodes, Java, Groovy, and Scala. So I got three programmers and three languages I created. These are the nodes. But remember, I'm interested more in the relationship between them. So I'm creating relationships. So what am I saying here? I'm saying Java, the language, is related to, in a programming in relationship, to whom? James. In other words, James is programming in Java. Sarah is programming in Java. James is learning Groovy. Sarah is learning Groovy. And Bill is learning Scala. So I've set up a relationship between these people, what they program in and what they are learning. The relationship here is between languages and people, right? Then I index on the node. In this particular case, I'm indexing on James and Sarah. So I'm done. I store the data in the database. So that gets committed. The database should have the data. Then I want to print the details. What am I going to do to print the details? I'm going to get a node, given a name. I don't know what name I'm going to ask for. But go get the data from the database. So I say node index get person name. Remember, by the way, before I go further, as I'm showing this to you, what have you not seen so far? No schema, right? There's no schema. I have not created any schema yet. There's no schema. It's purely the data that we are creating at this point and the relationship. So right there I say, here's the person that I've obtained from the database. Then I'm going to create a relationship. And the relationship I'm going to navigate through, I say for relationship in person.getRelationship. So for this particular person, get me all the relationships this person has. Print out the relationship type for me, whatever the relationship detail is. And then tell me the property for the language. The person who asked the question earlier, how do you know what it contains? You would have to base on your knowledge of the domain, knowledge of the problem, right? And if you don't know that you have a language property, notice it's called get property. This is Java code, right? You didn't say person.language. You didn't say person.something. You said get property. But that is a string. That is a string. So before you put that string, your application could go to the database and say, excuse me, can you tell me what relationships you have? Well, I've got a learn to program relationship, learn to watch movies relationship, a music relationship. Oh, so there are three relationships. Hey user, what would you like? I'm interested in music. Okay, I'll query for it. What if you turn the query into what the user wants, then hard coding in the program? You see where it's going? So this becomes very flexible because it's driven by the user interaction rather than hard coding in the code. So the user could come in tomorrow and say, can I drop a new relationship? And the code says, I'm not going to be rigid. I'll let you create new relationships on the fly. Then your application becomes very malleable, right? Very, very powerful. Testing is important, of course, right? So you got to write quite a bit of unit tests to make sure things work properly, but this gives you more flexibility. So given this, everyone doing that, and I'm going to go ask for the relationship of every person in this case. So again, I get all the relationship, but this time I go to the relationship, go to the language, and everybody who is doing that, jumping one more level. And then I print that. So here is the use data. I print all the details for James and all the details for Sarah, right? So those are the two things I'm going to ask for. So how is this going to work? Let's take a look at how this is going to work. I'm going to go ahead and compile and run this. So I just run Gradle. And when I run Gradle, I'm running Gradle in quiet mode here, that's all. And this is going to compile the source code and then run the source code. That's all it's going to do, right? Run the compiled code. So let's go through it. And once this runs, of course, it's going to display the relationship we created. That's all it's going to do in this particular example that we created. It's still warming up here. So how does this pan out? We want to know that James is programming in Java, but is learning Groovy, for example, and we want to take a look at all these relationships. It's probably, one of the things I like about Gradle is it'll go and install all your dependencies. So at this point, it's actually spending more time connecting to the internet to check for dependencies. That's why it's taking this long. And I hope my internet connection is actually working. Let me check. Otherwise, it's probably going to complain at this point. So let's see if that's true. Yeah, that's a little slow, but it's there. Okay. So anyway, so that is the type of relationship. We'll come back and take a look at this a little later. We won't wait for this. Let Gradle do its job. So we'll come back and check a little bit later. So what did we do here? We can create a relationship of these data, and then of course, they're not often clustered. Why are this not clustered? Unlike the other category, right? The aggregate-oriented often are clustered. This one is not. And the reason is because you want relationships more so. This goes to your question, the Stockholm Syndrome, right? Because this relationship is also essential for relational databases, and the clustering becomes painful when you start doing that. Because ad hoc queries become necessary at that point, and then clustering kind of becomes limitation. That's why you see that limitation here as well. And so optimize for a query on the relationship itself. And of course, you are looking at viewing node and edges in this particular case. So some databases in this area, Neo4j, Infinite Graph, FlockDB are some. What kind of data would you store in this? Social networking data, right? Twitter accounts, for example. You are following somebody who follows somebody who follows somebody, and you want to find your 6 degree of separation. There are companies doing this, by the way. Think about this for a minute. You are interested in breaking a market, and you want to do a sale. And if you're a sales guy, what do? You say, hey, I want to know if I'm somebody who knows somebody who knows somebody who knows Naresha. How can I find that? Well, I could go to Twitter, I could go to Facebook, and I could start with him and look at his relationship. Who all is following him? Right? It doesn't matter who he follows. It matters who is following him, because they know him, right? And then I can branch out from there and say, oh, she knows her, and she knows him, and he knows him, and he knows him. Now I have a marketing path to break through. So I can start talking to her about, hey, I need to get connected with this person. Can you route me through, right? So we could try to find a network, a relationship to break in. And there are companies already working on these kinds of products, by the way, where they're trying to mine and find out what kind of relationship I can break through Twitter, through Facebook, other social conversations. And we want, because what you really need is contacts. And you break through when, one of the most important things today is trust. You know somebody, you worked with them, and somebody comes to you and says, do you think I should hire this person? And usually you say yes or you better not, depending on the person, right? But at least that gives you some information point, and that can be a very valuable thing, and you can break through. Social networking is very important in that regard. Also, to manage these accounts, please. Neo4j doesn't. So again, the goal there is very different, right? So if you want clustering, you probably would want, normally, if the relationship is what you're managing, you probably don't want clustering for that information. Again, keep in mind, we're not saying all the data goes into this, just the relationships go into this, right? So you could have multiple NoSQL databases and have clustering for other things. But when you want to mine through the relationships, you probably don't want to have clustering in that. But keep the relationships only in that case. So generally the answer is it wouldn't scale very well for clustering. Yep. It is not. So good question. The question is how easy it is to switch between one database to another. It is generally not, because it's not a standardized SQL. It depends on from which to which you are going, but the general answer is don't assume that it's going to be that easy, right? So they're all, because the flavor is different. So given this, You can also look at relationships, location-specific details. A lot of times you want to know where somebody is, and based on their location, you want them to have access to other things around them. Maybe you want to do a sale for them saying, hey, while you're here, could we sell you a coffee shop next door? There's a bookstore next door, right? Relationships are very important. And so also broad relationship, for example, hey, the guy who bought this book also bought this other book and this video, would you be interested? I want to talk a little bit about a few other things that are important to understand here. So, and those basically, this is stuck obviously for the connection, I think, so pardon me on that. So, so graph databases can handle ACID transactions fairly well, just like relational databases can. Aggregate databases normally only provide the consistency at the aggregate, the ACID at the aggregate level. What about consistency, by the way? Well, the problem with consistency is when you have this data across multiple clusters, they provide what is called eventually consistent, not instantaneously consistent. Now, you may say, wait a minute, that is bad because I change the data and I query and it is not there. That is not fun at all. Well, that is not true. We have to know what we are looking at. So if I'm putting money into a bank and I look back at the bank and the money is not there, I'll freak out. But on the other hand, you and I are on the phone and you say, hey Venkat, I saw this particular blog, they talked about this particular item, I just commented on the blog. And I immediately go look at the blog and say, where did you comment? I don't see it. Oh, you know what, check back, it'll be there, right? It's eventually consistent, it's not earth-shaking, you don't need that to be instantaneous at the moment. And so the point really is that you don't want it to be consistent instantaneously. Now, where does this really come in? Goes back to the failover. So what I can do is I can say, node 1 contains all this data, but I'm going to replicate it on node 2 for failover. Node 2 contains data for all these people, but I'm going to replicate it on node 3 for failover. I could have failovers in another node, maybe a slave node and a master node. And why am I doing this? Because if this node goes down, I can then get the availability in the other one, right? So, but of course, in this case, if I'm updating it, I'm going to send the update request, but I cannot guarantee consistency across these two right away, and there's going to be a little delay. So its eventual consistency comes into this. So this brings us to something very important for us to keep in mind. It's called the reverse conjecture or the CAP theorem. This theorem is very important. Pardon me, I have to get through, but I'll get to you in a minute. So the thing about this Bloom theorem, it really changes the way we look at it. In other words, if you say, this is what I want, I will not change what I want, then your choices are limited. But if you say, let me evaluate the options I have and choose what is the best for me, then you have a better handle on things. For example, what this says is, it's impossible for a distributed system to simultaneously guarantee all the three of the following: consistency, availability, and partition tolerance. What does that mean? Consistency, of course, means that data updates are consistent. Availability means you will get the data all the time when you need it. You won't have a downtime. And partition tolerance means you got a network split and you cannot access the other server, but you still should be able to tolerate that. Of these three things, you cannot have all the three all the time. And you need to design around these, right? And you need to ask yourselves, of these three, which two is the most important for you? And design for it. And if you try to design for all the three, you won't have any of those, right? So the point really is you got to pick and choose between these three. So the common theme really in NoSQL is sacrifice consistency just a little bit so that you can get a faster response and you can scale very well as well. That is really the goal of this. So what are the consequences of this? The consequence is that NoSQL basically is no schema, so you don't do any look-ahead planning for this. It is easy to make a change to this, of course. However, it is not as easy to have multiple database applications coming in. Each record contains whatever you care about, right? So you're not burdening yourself to say, you got to sit there and do a pre-planning and impose every row to have the same thing. You don't have that requirements. There is really no actual schema, but there's an implicit schema all the time. And your schema is in your mind, your schema is in the code, your schema is in the unit test. So there is a schema, but there's no explicit schema, and definitely not a published schema that you impose on other applications. Your DB cannot validate the data most of the time, and there's no clear structure, so this becomes really a problem if you want to share this across. It is very hard to span this across applications, so that is why I kept emphasizing this is not intended for enterprise database, this is intended for application database. So if you want to go through other applications, it will be a problem. If you want other applications to access the data, you still can, but you normally go through a gateway, meaning I'll put a web service in front of it, and you can come to me, I'll provide access to it, but I cannot open up this database for you to access, because when I change it, you're in trouble, right? So that's the way you can provide access to other systems. So I hope this gives you an idea about what NoSQL really is and isn't. It is not just one thing. It is these two types with these four subcategories, and it really is intended to solve a problem in a very pragmatic way. The essential thing to take away is this: you don't want to say, we will use NoSQL. It is a question of what combination of databases you're going to use. So typically I would say you would probably use a combination of databases, some relational and some not, and put them together as it would make sense. And you want to build the application through these things. The essential idea is this: you want to create something very lightweight that serves your problem, rather than being forced into following a rigid structure that becomes hard to maintain. So that's all I have. Thank you.